Hello, friend. Welcome back to another quiet journey through the cosmos. Some nights the sky feels heavier than it should. Stars breathe slower. Time folds in silence. Maybe that's just the mind listening to the universe's oldest whispers. Tonight, we're going to watch something most people never think about. We're going to watch stars grow old. Not collapse, not explode, not die in violence. Just grow old. Gently, beautifully, impossibly large. These are the red giants, the elders of the cosmos, stars, in their final act before the curtain falls. And what they become in those last moments might be the most extraordinary transformation in all of nature. Before we drift into this story, if you find comfort in these quiet explorations of the universe, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. Now let's begin. Picture this. Right now, somewhere about 640 light years from where you're resting, there's a star called Betelgeuse. You've probably seen it. It marks the shoulder of Orion, that hunter constellation stretched across winter skies. Betelgeuse is so large that if you placed it where our sun sits, it would swallow Mercury, Venus, Earth, and Mars whole. Its surface would reach somewhere past the asteroid belt. And yet, despite being nearly 1,000 times wider than our sun, Betelgeuse is cooler. Its surface glows at only about 3,500 degrees Celsius compared to the sun's 5,500. It shines red like embers in a dying fire. This is what astronomers call a red giant, a star that has grown impossibly vast and strangely gentle at the end of its life. But here's what makes this beautiful. Betelgeuse wasn't always this way. 10 million years ago, it was smaller, hotter, burning blue-white like a young star should. It spent millions of years in what scientists call the main sequence, that stable middle age of stellar life, where fusion happens quietly, steadily in the core. Hydrogen atoms smash together under unimaginable pressure and heat, fusing into helium, releasing energy that pushes outward against gravity's inward pull. Balance, equilibrium. The star stays the same size, the same temperature for eons. Our sun has been doing this for 4.6 billion years. It will continue for another 5 billion. But nothing lasts forever, not even stars. Scientists suggest that when a star like our sun or larger stars like Betelgeuse begin to run low on hydrogen in their cores, something shifts. The fusion slows. The outward pressure weakens. And gravity, patient gravity, begins to win. The core contracts, squeezing tighter, heating up from the compression. Meanwhile, the outer layers of the star, those vast shells of hydrogen that never got hot enough to fuse, suddenly find themselves sitting atop a furnace that's growing hotter. A shell of hydrogen around the core ignites. It starts fusing. And here's the strange part. That shell fusion is more violent, more energetic than the steady core fusion ever was. It pumps tremendous energy outward. The star's outer layers absorb that energy and do the only thing they can. They expand, they swell, they balloon outward, growing larger and larger, even as the core inside shrinks smaller and smaller. Research shows this expansion happens over millions of years for massive stars, but it can take 1 billion years or more for stars closer to our sun's size. The outer layers stretch so far from the core that they cool down. Heat spreads thin across an enormous surface area. The star's color shifts from white or yellow or blue to orange, then red. It becomes a red giant, not because it's hotter, because it's cooler. This is one of the most common misunderstandings about stars. We think bigger means more powerful, more intense. But in the language of dying stars, bigger often means gentler, softer, fading. There's a woman named Cecilia Payne who changed everything we know about stars. In 1925, at a time when women weren't even allowed to be listed as authors on Harvard research papers, she wrote a doctoral thesis that revealed something radical. Stars, she demonstrated, are made mostly of hydrogen and helium, not the heavy elements we find on Earth. Her professors dismissed her findings. They said it was impossible. But she was right. She had unlocked the secret of what stars are made of, and therefore what they burn. Her work laid the foundation for understanding stellar evolution, for knowing that when hydrogen runs out, stars must change, must evolve, must become something else. The astronomer Otto Struve later called her thesis the most brilliant ever written in astronomy, and yet, for decades, her contributions were barely acknowledged. The universe keeps its secrets until someone brave enough listens closely. Think about our sun for a moment. Right now, it's fusing about 600 million tons of hydrogen into helium every single second. Every second. That helium sinks to the core, building up like ash in a fireplace. One day, about 5 billion years from now, there won't be enough hydrogen left in the core to sustain fusion. The core will contract. The outer hydrogen shell will ignite, and our sun, our steady, reliable sun, will begin to grow. It will expand past Mercury's orbit, then Venus. Some models suggest it might reach Earth's orbit, though our planet will likely have already spiraled outward from tidal forces. The sun will become a red giant, glowing soft and orange, filling half the sky if anyone were still here to see it. It seems impossible, doesn't it? That something so constant could change so completely. The timeline of stellar death depends on mass. Massive stars, those 10, 20, 50 times heavier than the sun, burn through their fuel fast. They live only a few million years before becoming red supergiants like Betelgeuse. Medium stars like our sun take billions of years. The smallest red dwarf stars, with only a fraction of the sun's mass, burn so slowly they could live for trillions of years. The universe isn't old enough yet for a single red dwarf to have died of old age. Not one. Every red dwarf ever born is still burning somewhere out there waiting. But when stars like the sun reach the end, they don't go quietly into darkness. They bloom, they swell, they become something vast and strange and red. It seems as though the universe has a rhythm to it, a pattern written into physics and time. Stars are born from collapsing clouds of gas they ignite. They burn steady for eons. And then when the fuel runs low, they transform. They don't simply fade, they grow. They become giants, red giants. And in that growth and that swelling, they begin to create the elements that will one day form planets, atmospheres, oceans, life. Carbon, nitrogen, oxygen, the ingredients of everything you are. But we'll come to that soon. For now, just rest in this thought. Somewhere tonight, a star is swelling. Its core is shrinking, compressing, heating. Its outer layers are drifting outward, cooling, glowing red. It's becoming something larger than it ever was, softer than it ever was, and somehow in its gentleness, more powerful than we can imagine. Red giants are not the end. They are the beginning of the end, and that beginning is more beautiful than the brightness that came before. You don't need to understand everything. Just rest and let curiosity do the listening. We've only just begun to watch stars grow old. There's so much more to see. But before a star becomes a giant, before it swells and reddens and transforms, it must survive something violent, something hidden. A flash of fire in the core that no one can see from the outside, a detonation so powerful it could tear the star apart, and yet somehow it holds. That moment, that helium flash, is where we're drifting next. There was a time long before stars grew gentle and red, when they burned with a clarity that could cut through the darkness of space. Young stars, fierce and focused, living in a kind of mathematical perfection. Balance, pressure against gravity, light against collapse. This is where every red giant begins in that golden age of stellar life called the main sequence. And to understand what happens when a star dies, we must first understand what it means for a star to live. Imagine you could rewind time back 4.6 billion years to a cloud of gas and dust collapsing under its own weight. Gravity pulls it inward tighter and tighter until the center grows so hot, so dense, that hydrogen nuclei, those single protons, begin to collide with enough force to overcome their natural repulsion. They fuse. 4 hydrogen atoms become 1 helium atom, releasing energy in the form of light and heat. This is nuclear fusion, the engine that powers every star in the sky. And once it begins, something extraordinary happens. The energy released pushes outward, creating pressure that balances perfectly against gravity's inward pull. The star stops collapsing. It stabilizes. It enters the main sequence. For stars like our Sun, this balance can last 10 billion years. For more massive stars, only a few million. But while it lasts, it is steady, predictable, a kind of cosmic peace. Scientists call this balance hydrostatic equilibrium. It's a term that sounds technical distant, but it describes something deeply beautiful. Every layer of the star, from the core to the surface, sits in perfect tension between the weight pressing down and the pressure pushing up. If fusion slows even slightly, gravity wins, and the core contracts, which heats it up, which speeds up fusion again. If fusion speeds up too much, the extra pressure pushes outward, cooling the core, slowing fusion back down. The star regulates itself. It's a kind of breathing slow and steady that keeps a star alive for eons. Our Sun fuses about 600 million tons of hydrogen every second. And yet, it's been doing this for nearly 5 billion years without running out. Do you ever think about that? How something can burn so intensely for so long and still hold itself together? The main sequence isn't a place, it's a phase. A chapter in a star's life where fusion in the core is steady, where hydrogen turns to helium in a slow, controlled burn. On a chart called the Hertzsprung-Russell diagram, which plots stars by brightness and temperature, the main sequence appears as a diagonal band, stretching from hot, bright blue stars in the upper left to cool, dim red dwarfs in the lower right. About 90% of all stars in the universe sit somewhere along this band. Our Sun is right in the middle, a yellow dwarf, ordinary in almost every way, except for the fact that it sustains life on a small blue planet orbiting in its habitable zone. But even ordinariness has limits. Even the Sun will leave the main sequence one day. There was a woman named Cecilia Payne-Gaposchkin, who in 1925 discovered what stars are truly made of. At the time, astronomers assumed stars had roughly the same composition as Earth, rich in metals like iron and silicon. But Payne analyzed the spectra of starlight, those fingerprints of color that reveal which elements are present, and she concluded something radical. Stars are made almost entirely of hydrogen and helium. Her thesis advisor, Henry Norris Russell, told her the result was impossible. He convinced her to soften her claims. Years later, Russell independently confirmed her findings and is often credited for the discovery, even though Payne did the work first. It wasn't until decades later that her contribution was properly recognized. She became the first woman to head a department at Harvard, but only after years of being paid less than her male colleagues and denied the title of professor. Her story reminds us that science doesn't just happen in laboratories and telescopes. It happens in the quiet courage of people who see what others refuse to believe. Her discovery unlocked the secret to stellar evolution. If stars are mostly hydrogen, then their life cycle depends on how long the hydrogen lasts. And the irony is, the bigger the star, the shorter it lives. A star 10 times more massive than the Sun burns 1,000 times brighter and exhausts its hydrogen in only 20 million years. A star half the Sun's mass can burn for 80 billion years or more. The smallest stars, red dwarfs, with only 8% of the Sun's mass, burn so slowly they could theoretically last for trillions of years. The universe is only 13.8 billion years old, which means not a single red dwarf has ever died of old age. Every one of them, billions upon billions, is still on the main sequence, still fusing hydrogen, still waiting. But our Sun is different. It's middle-aged now, about halfway through its main sequence life. In its core, hydrogen is still abundant, still fusing steadily into helium. That helium doesn't fuse not yet. It's too cool, too low in pressure. so the helium just accumulates, sinking to the center, building up like ash in a furnace. Slowly, over billions of years, the core becomes more and more helium-rich, and the hydrogen burns in a thinner and thinner shell around it. Research shows that as this happens, the core contracts slightly under its own weight, which increases the temperature and pressure, which makes the hydrogen fusion burn a bit hotter, which makes the sun a bit brighter. Our sun today is about 30% brighter than it was when it first formed. In another billion years, it will be bright enough that Earth's oceans will boil away. But that's still the main sequence, still stable, still balanced. The end begins quietly. One day, billions of years from now, the hydrogen in the sun's core will run low. Not gone, just scarce enough that fusion can't sustain the outward pressure. And when that pressure drops, gravity takes over. The core begins to contract. As it contracts, it heats up from the compression the same way a bicycle pump gets warm when you squeeze air into a tire. The core grows hotter and hotter, but it's no longer fusing hydrogen because there's almost none left there. Instead, a shell of hydrogen just outside the core hydrogen that was never quite hot enough to fuse before suddenly finds itself in a furnace. It ignites. Shell burning begins. And here's the paradox. Shell fusion is more energetic than core fusion ever was. It releases more energy, more heat, more pressure. That energy pushes the outer layers of the star outward. The sun begins to swell. The main sequence ends. The red giant phase begins. It seems as though nature has a strange sense of irony. The moment a star starts to die, the moment its core runs out of fuel, is the same moment it grows larger than it has ever been. This isn't unique to stars. Think about a candle. When the wax runs low, the flame often flickers brighter, burns hotter for just a moment before going out. Or think about how autumn leaves turn brilliant red and gold just before they fall. Endings can be the most vivid moments of existence. For stars, the end of hydrogen in the core isn't the end of light. It's the beginning of transformation. Let's compare. A star like Sirius, the brightest star in our night sky, is about twice the mass of the sun. It's currently on the main sequence, burning hydrogen steadily in its core. It will stay there for about another 600 million years. When its hydrogen runs out, it will become a red giant for only a few million years, a brief flicker of expansion, before it sheds its outer layers and becomes a white dwarf. Meanwhile, a star like Proxima Centauri, the closest star to our sun, has only 12% of the sun's mass. It will remain on the main sequence for 4 trillion years. By the time Proxima Centauri becomes a red giant, if it ever does, the universe will be so old, so dark, that most galaxies will have drifted beyond the reach of light. Stellar evolution happens on timescales so vast they almost feel like fiction. And yet, we know these things. We've watched stars at different stages of life. We've seen newborn stars wrapped in cocoons of gas main sequence stars, burning steady red giants, swollen and glowing white dwarfs, cooling slowly in the dark. We've built computer models that simulate millions of years of fusion, contraction, expansion. We've tested those models against observations, refining them, learning. Some believe that understanding how stars live and die is one of humanity's greatest achievements, not because it gives us power, but because it gives us perspective. We are small, brief, and yet we can look up at a star and know its past, its future, its fate. The main sequence is the longest, most stable phase of a star's life, but it doesn't last forever. Nothing does. When the hydrogen runs out, when the core contracts and the shell ignites, the star leaves behind the life it has known for billions of years. It steps into something new, something vast, something red. But between the main sequence and the red giant, there is a moment hidden deep in the core where something violent happens. Something most people never hear about. A flash, a detonation. A runaway fusion event that releases as much energy in a few seconds as the sun releases in 100 million years. And somehow, impossibly, the star survives. That flash is waiting for us, quiet and hidden just ahead. Deep inside a dying star in a place no telescope can see, something waits, a core of helium compressed inert, growing hotter with every passing million years. It doesn't glow, it doesn't burn, it just waits pressed tighter and tighter by gravity until one day, without warning, it ignites. Not gradually, not gently, all at once. In a single catastrophic flash that releases more energy in seconds than our sun will produce in 100 million years. And yet, from the outside, nothing changes. The star doesn't brighten, doesn't flicker. The surface knows nothing of the violence happening at its heart. This is the helium flash, one of the most dramatic events in stellar evolution, and also one of the most invisible. Let's go back to that moment when the main sequence ends. The hydrogen in the core has run out. The core is now made almost entirely of helium, the ash left behind, from billions of years of fusion. That helium sits there dense and hot, but not hot enough to fuse. Not yet. Helium fusion requires temperatures around 100 million degrees Celsius, nearly 10 times hotter than hydrogen fusion. So, the core just contracts under gravity, slowly squeezing tighter, heating up degree by degree, century by century, while a shell of hydrogen above it burns furiously, pushing the star's outer layers outward into a red giant. The core shrinks, the star swells. This can go on for hundreds of millions of years, but eventually the core reaches a critical threshold. It gets hot enough. And when it does, helium begins to fuse. Scientists suggest that helium fusion happens through a process called the triple alpha process. 3 helium nuclei, each containing 2 protons and 2 neutrons, called alpha particles, collide and stick together to form a single carbon nucleus. It's an incredibly unlikely reaction. The first 2 helium nuclei have to collide and briefly form an unstable isotope of beryllium, which exists for only a fraction of a second before falling apart. But if in that tiny sliver of time, a 3rd helium nucleus happens to collide with the beryllium, it stabilizes into carbon. It sounds almost impossible, and yet it happens constantly in the cores of evolved stars. Sometimes a 4th helium nucleus fuses with the carbon to make oxygen. This is how the universe creates the building blocks of life. Carbon and oxygen forged in the hearts of dying stars. But here's where things get strange. In stars like our sun, stars with masses between about 1/2 and 2 solar masses, the helium core becomes something unusual before it ignites. It becomes what physicists call electron degenerate. This is a quantum mechanical state where electrons are packed so tightly that they resist being squeezed any further, not because of heat or pressure in the normal sense, but because of the Pauli exclusion principle, a rule of quantum mechanics that says, no, 2 electrons can occupy the same state. The electrons push back against gravity, not with thermal pressure, but with degeneracy pressure. And here's the problem. Degeneracy pressure doesn't depend on temperature. In a normal gas, if you heat it up, it expands and cools itself down, creating a kind of natural thermostat. But in degenerate matter, heating doesn't cause expansion. The pressure stays the same. So, when helium fusion finally ignites in a degenerate core, the heat can't escape. The temperature skyrockets. Fusion accelerates. More heat, more fusion, more heat. It's a runaway reaction, a thermonuclear explosion, the helium flash. Research shows that during the helium flash, the core's temperature can spike to hundreds of millions of degrees in a matter of seconds. The energy released is staggering, equivalent to the entire luminosity of a galaxy for just a brief moment. And yet, all of that energy is absorbed by the surrounding layers of the star. The outer envelope is so massive, so thick, that it cushions the blast. The core expands slightly from the energy, which breaks the degeneracy, which allows normal thermal pressure to take over, which stabilizes the fusion. Within minutes, the runaway reaction stops. The core settles into a steady helium-burning phase. And from the outside, an observer watching the star would see absolutely nothing. No flash, No brightening, no change at all. The explosion happens in silence, hidden beneath a billion kilometers of stellar atmosphere. Think about that for a moment. An event powerful enough to outshine a galaxy contained entirely within a star, invisible to the universe. It's like a scream in a soundproof room. The violence is real, the energy is real, but no one hears it, no one sees it. For decades, astronomers debated whether the helium flash even happened. It was predicted by theory in the 1950s. But how do you observe something that leaves no trace? The person who first worked out the physics of the helium flash was a physicist named Fred Hoyle in the early 1950s. Hoyle was brilliant and controversial, a man who coined the term Big Bang as a way to mock the theory he didn't believe in, even though the name stuck and the theory turned out to be correct. But Hoyle's work on stellar nucleosynthesis, how elements are formed inside stars, was groundbreaking. He and his colleagues showed that carbon, nitrogen, oxygen, and many other elements are created through nuclear fusion in stars not during the Big Bang. And he predicted the existence of a specific excited state of carbon that would allow the triple alpha process to happen efficiently. Observations later confirmed that state existed exactly as he had predicted. Hoyle should have won the Nobel Prize for this work. Many scientists believe he deserved it, but he never did. Sometimes the universe doesn't reward the people who see its secrets first. Later in the 1960s and 70s, a Japanese-American astrophysicist named Iko Eben Jr. built detailed computer models of stellar evolution and confirmed that low-mass stars undergo a helium flash. Eben's models track stars through millions of years of simulated time, calculating temperatures, densities, fusion rates at every stage. His work showed that the helium flash is brief, violent, and completely hidden. It's a reminder that some of the most important events in the universe happen far from view, in places we can never directly observe. We know they happen because the math says so, because the models predict them, because when we look at stars in later stages, they match what we'd expect if the flash had already occurred. Not all stars experience a helium flash. Stars more massive than about 2 solar masses don't develop degenerate cores. Their cores are hot enough that helium ignition happens smoothly without a runaway. They transition from hydrogen shell burning to helium core burning, gradually, almost peacefully. It's only the smaller stars, the sun-like stars, that experience this hidden violence. And there's something poetic about that. The quiet, ordinary stars, the ones that live longest and burn steadiest, are the ones that carry the most dangerous secret in their cores. Some believe the helium flash is what prevents low-mass stars from collapsing into black holes or exploding as supernovae. The flash releases just enough energy to halt the core's contraction, to stabilize it, to give the star a second life-burning helium instead of hydrogen. Without the flash, the core might keep contracting until electron degeneracy could no longer support it, until it collapsed into something stranger, denser, darker. But the flash saves it for a little while longer. After the helium flash, the star settles into a new equilibrium. The core is now burning helium into carbon and oxygen through the triple alpha process. The hydrogen shell above it continues to burn. The star actually shrinks a little from its red giant size and becomes slightly hotter and bluer again. Astronomers call this the horizontal branch phase because on the Hertzsprung-Russell diagram, these stars form a horizontal line across the chart. The star can spend around 100 million years in this phase, a brief encore compared to the billions of years it spent on the main sequence, but still a significant chapter in its life. It's a kind of middle age, a second stability before the final act. But even this doesn't last. Eventually, the helium in the core runs out just as the hydrogen did before. The core contracts again. A shell of helium ignites around it, and above that, the hydrogen shell continues to burn. The star has 2 shells of fusion now layered like an onion. And this time, when the core contracts, there's no degeneracy pressure to save it, no flash to reignite it. The star enters its final phase, a phase where it will pulsate, shed mass, and create some of the most beautiful structures in the universe. But that comes later. Right now, we're still in the aftermath of the flash, in that moment when the core has just ignited and the star has found a fragile temporary peace. Have you ever wondered what it would be like to witness something so powerful that it could destroy a planet and yet remain completely invisible? The helium flash is that paradox. It's the moment when a star's death becomes irreversible, when the countdown truly begins, and yet it happens in perfect silence. The core burns, the star holds, and the universe moves on unaware. It seems as though stellar evolution is full of these quiet turning points, moments where everything changes and nothing shows. The helium flash is the heart reigniting one last time before the final expansion begins. And when that expansion comes, when the star grows larger than it has ever been, it won't be because of an explosion. It will be because the fusion in the core and the shells is pushing outward with such force that the star has no choice but to swell, to stretch, to become something vast and red and strange. That swelling is what we turn to. Now, the great expansion, the moment when stars become giants in the truest sense. There's a star in the constellation Taurus, glowing soft and orange in the winter sky, that used to be small, smaller than it is now. Millions of years ago, Aldebaran was a main sequence star, compact, efficient, burning hydrogen in its core. Today, Aldebaran is 44 times wider than our Sun. If you placed it where the Sun sits, its surface would extend past the orbit of Mercury, swallowing the innermost planet whole. And yet, despite being so enormous, Aldebaran's surface is cooler than the Sun's. It glows at only about 3,900 degrees Celsius. It's a red giant, a star that has grown vast, not because it's hotter, but because it's dying. This is the great expansion, the moment in a star's life when everything we think we understand about size and heat stops making sense. Bigger doesn't mean fiercer. Larger doesn't mean brighter in the way you'd expect. When a star runs out of hydrogen in its core and begins burning it in a shell, when the energy from that shell fusion pumps outward with relentless force, the star's outer layers have no choice but to respond. They expand, they swell, they grow so large that the star transforms from a compact ball of fire into something diffuse, enormous, ghostly. And in that transformation, the surface cools. The color shifts from white or yellow to orange, then red. The star becomes gentle even as the forces inside it grow more violent. Let's trace this carefully, step by step, because the physics here is beautiful and strange. After the helium flash, or in more massive stars, where helium ignites smoothly, the core is now burning helium into carbon and oxygen. Above the core, a shell of hydrogen continues to fuse into helium. That shell burning is powerful, more energetic than the core fusion ever was. It releases a tremendous amount of energy, and that energy has to go somewhere. It pushes outward into the layers of gas above it. Those outer layers absorb the energy and expand. They move farther and farther from the core, ballooning outward. As they expand, they cool because the same amount of heat is now spread across a much larger surface area. Think of it like stretching a blanket. The more you pull it, the thinner it gets, the less warmth it holds in any one spot. The star's surface temperature drops. And when the surface temperature drops below about 5,000 degrees Celsius, the light it emits shifts toward the red end of the spectrum. The star turns red. Scientists suggest that this expansion happens over the course of several 100 million years. For stars like the Sun, though, for more massive stars, it can happen much faster. The outer envelope swells to hundreds of times its original size. In the case of our Sun, when it becomes a red giant about 5 billion years from now, it will expand to roughly 200 times its current radius. That means its surface will reach somewhere between the orbits of Earth and Mars. Earth itself will likely be engulfed, or at the very least scorched beyond recognition. The oceans will boil away. The atmosphere will be stripped. The planet will become a lifeless molten rock if it survives at all. And all of this will happen slowly over millions of years as the sun grows larger and cooler and redder. But here's the paradox. Even though the surface is cooler, the red giant is often much more luminous than the star was on the main sequence. Luminosity depends on both temperature and surface area. A red giant has a lower surface temperature, yes, but it has so much more surface area that it can still outshine its younger self by hundreds or even thousands of times. Betelgeuse, that massive red supergiant in Orion, is about 100,000 times more luminous than the sun, even though its surface is cooler. It's as if the star is compensating for its cooling by simply becoming larger, more space to radiate from, more light even if each part of the surface is dimmer. This is one of the most common misunderstandings about stars. We assume hotter means brighter, bigger means more powerful. But stellar evolution doesn't follow our intuitions. A red giant is cooler than it was, less dense. Its outer layers are so tenuous that they're almost like a vacuum by Earth standards. And yet, it's still a star, still fusing elements, still holding itself together through a balance of gravity and pressure. It's just doing it in a way that looks almost fragile, almost ghostly. Let's look at a real example. Arcturus, the brightest star in the constellation Boötes, is a red giant about 25 times the diameter of the Sun. It's 170 light-years away, close enough that ancient astronomers observed it and noted its reddish hue. Arcturus is cooler than the Sun, with a surface temperature around 4,300 degrees Celsius, but it's about 170 times more luminous. Research shows that Arcturus is likely in the horizontal branch phase, burning helium in its core and hydrogen in a shell, having already survived its helium flash. In a few tens of millions of years, Arcturus will exhaust its helium swell even larger and begin shedding its outer layers. But right now, it's stable glowing, steadily a quiet giant in the night sky. Or consider Antares, the red supergiant in Scorpius. Antares is so large that if you placed it at the center of our solar system, its surface would extend past the orbit of Mars, possibly reaching the asteroid belt. It's about 12 times more massive than the Sun, and because of that mass, it burns through its fuel much faster. Antares has already left the main sequence already swelled into a supergiant, and it's approaching the end of its life. In astronomical terms, it could explode as a supernova any time in the next million years, maybe sooner. When it does, it will briefly outshine the entire galaxy. But for now, it just glows red and enormous, a reminder that even the most massive stars have a phase where they grow soft and cool before their violent end. The timeline of expansion varies wildly depending on the star's mass. A star like the Sun will spend about 1 billion years as a red giant, swelling and contracting slightly in phases as it burns through helium and hydrogen in shells. A more massive star, 10 or 15 solar masses, might only spend a few million years as a red supergiant before running through all its fusion fuel and collapsing into a supernova. The smallest stars that can become red giants, those just barely massive enough to ignite helium, will take the longest lingering in the red giant phase for billions of years. It's a strange inversion. The stars that live longest often die slowest, stretching out their final chapters over eons. There's a phrase in astronomy, giants are not fierce, they are fading. It captures something essential. When we think of giants, we think of strength, power, dominance. But red giants are the opposite. They are stars and retreat stars that have lost the battle against gravity and time, and are now giving up their outer layers, puffing up into something enormous but fragile. The core inside is still burning, still fighting, but the surface has already begun to drift away. It's a kind of surrender, slow and graceful. One of the mistakes people make is assuming that red giants are rare or exotic. In truth, they're a natural stage in the life of most stars. Every star between about 0.5 and 8 solar masses will become a red giant at some point. That includes the Sun. That includes billions of other stars in our galaxy alone. Right now, at this very moment, there are countless red giants scattered across the Milky Way, swollen and red, slowly shedding their outer layers into space. We just don't notice them because space is so vast, because most of them are too far away to see with the naked eye. But they're there, breathing slowly, fading gently. Some believe the red giant phase is when stars do their most important work. Not the brightest work, not the most dramatic, but the most essential. Because it's in this phase that stars begin to enrich the interstellar medium with heavier elements. The hydrogen and helium they were born with has been transformed through fusion into carbon, nitrogen, oxygen, and other elements. And as the star swells, as its outer layers grow more diffuse, those elements begin to escape. The star starts to lose mass-blowing material out into space through what's called a stellar wind. That wind carries carbon and oxygen and nitrogen, the building blocks of planets' atmosphere's life itself. The red giant phase is where the universe starts recycling its matter, where the elements forged in stellar cores begin their journey into the cosmos. But that wind, that mass loss, is something we haven't fully explored yet. It's not just a gentle breeze. It's a relentless, powerful flow of particles and gas driven by radiation pressure and pulsations in the star's outer layers. Research shows that a red giant can lose a significant fraction of its total mass during this phase, sometimes 20%, 30%, even more. The wind carries that mass away at speeds of tens of kilometers per second, creating vast shells and clouds of gas around the star. And in those clouds, in that diffuse material, new stars can eventually form. Stellar nurseries seeded by the death of older stars. It's a cycle slow and vast, connecting generations of stars across billions of years. Do you ever look up at the sky and wonder which stars are near the end? Which ones are swelling, cooling, preparing to shed their outer layers and fade into something smaller, quieter? You can't tell just by looking. A red giant might appear, steady, unchanging, glowing calmly in the night. But inside, and just beyond its surface, the transformation is already underway. The expansion has begun. The mass is drifting away. And soon, very soon, in cosmic terms, the wind will grow stronger, the star will pulse and brighten and dim, and the outer layers will start to peel away like petals from a flower. That wind, that slow, steady loss of self, is where we're drifting now. Imagine standing on a world orbiting a red giant, if such a thing were possible. You'd look up and see a sun so vast it fills half the sky, glowing dull orange like a coal losing its heat. And if you watch carefully over years and centuries, you'd notice something strange. The star is shrinking, not collapsing, not dimming, just slowly giving itself away. Atom by atom, molecule by molecule, the outer layers are drifting into space, carried on an invisible wind that never stops, never rests. This is the stellar wind, a river of matter flowing outward from dying stars. And it's one of the most important processes in the universe. Because stars don't just fade, they give themselves back to the cosmos, piece by piece, until there's almost nothing left. Every star produces a stellar wind. Even our sun right now is losing mass. The solar wind carries about 1 million tons of material into space every second. That sounds like a lot, but over the sun's entire 10 billion year lifespan, it will lose less than 0.01% of its total mass this way. It's negligible, a whisper, barely noticeable. But when the sun becomes a red giant, that whisper becomes a howl. Research shows that red giants can lose mass at rates 10,000 to 100,000 times stronger than the sun does now. Some lose 1 million times more. Over the course of just a few 100,000 years, a red giant can shed 20%, 30%, even 50% of its total mass. The star literally dismantles itself layer by layer until only the core remains. Why does this happen? What drives the wind? The answer lies in radiation pressure, the force of light itself, pushing against matter. Deep inside, the star fusion produces enormous amounts of energy in the form of photons, particles of light. Those photons travel outward, bouncing and scattering through the dense stellar interior. And when they reach the outer layers, where the gas is thin and cool, they start to push. Photons carry momentum, And when they collide with atoms and dust grains in the star's atmosphere, they transfer that momentum outward. If the radiation pressure is strong enough, it can overcome gravity. The atoms accelerate, they escape, they drift into space. Scientists suggest this process is especially effective in red giants because their outer layers are so diffuse, so loosely bound by gravity that even a modest push can set them free. But there's more to it than just photons. Red giants also pulsate. Their outer layers expand and contract rhythmically, like a slow heartbeat driven by instabilities in the way energy flows through the star. When the layers expand, they cool and become more transparent, allowing radiation to escape more easily. When they contract, they heat up and become more opaque, trapping radiation. This creates a cycle, a rhythm, and with each pulse, a little more material gets kicked outward, lifted just far enough that the radiation pressure can take over and carry it away. The pulsations act like a pump, feeding the wind, making it stronger and more persistent. Let's look at a real star. I.K. Tauri, a red giant about 260 light-years away. In the constellations, Taurus has been studied extensively with radio telescopes, particularly the Atacama Large Millimeter Array, or ALMA, in Chile. Observations show that I.K. Tauri is surrounded by a vast, complex shell of gas and dust material that the star has been shedding for thousands of years. The wind from I.K. Tauri is moving at about 20 kilometers per second, which might not sound fast, but over time that wind has created a bubble of material stretching billions of kilometers across. Inside that bubble, astronomers have detected molecules like carbon monoxide, water vapor, and silicon monoxide, evidence that the star is enriching the surrounding space with heavy elements forged in its core and shells. Some believe I.K. Tauri will eventually become a planetary nebula, one of those glowing shells of gas that mark the final chapter of a red giant's life. But we're not there yet. Right now, I.K. Tauri is still in the mass loss phase, still breathing out its substance into the void, still clinging to the last remnants of fusion in its core. The wind will continue for tens of thousands of years, maybe longer, until the star has lost so much mass that it can no longer sustain the outer envelope. And then, only then, will the core be exposed and the real beauty will begin. The mass loss isn't uniform. It doesn't flow out evenly in all directions. Research shows that stellar winds from red giants can be clumpy, asymmetric, shaped by magnetic fields, rotation, or the presence of a companion star. Some red giants lose mass in great blobs and streamers, creating intricate, chaotic structures around them. Others produce spiral patterns like water flowing from a rotating sprinkler because the star is spinning and dragging its wind around with it. And in binary systems where a red giant orbits another star, the wind can be funneled, focused, creating arcs and bridges of gas between the two stars. The universe is messy, and stellar winds reflect that messiness. There's a star called Mira, about 300 light-years away in the constellation Cetus. Mira is a pulsating red giant, one of the most famous variable stars in the sky. Its brightness changes over a cycle of about 332 days, dimming and brightening as it pulses. But Mira is also losing mass, and it's doing so in a spectacular way. Observations from ultraviolet telescopes have revealed that Mira is racing through space at about 130 kilometers per second. And as it moves, its stellar wind is being left behind, creating a tail of glowing gas that stretches for 13 light-years. 13 light-years. That's more than 3 times the distance from the Sun to the nearest star. Mira is shedding itself across an almost incomprehensible distance, leaving a trail of stardust in its wake, like a comet made of atoms. Think about what that means. The material Mira is losing today, the carbon and oxygen and nitrogen it's breathing out, will drift through space for millions of years. Eventually, it might encounter a cloud of gas and dust, a stellar nursery where new stars are forming. That material will mix with the primordial hydrogen and helium, enriching it, adding complexity. And one day, a new star might form from that cloud, a star that contains atoms forged inside Mira. Planets might form around that star. Life might arise. And none of it would have been possible without Mira's wind, without the slow, patient loss of mass that scattered those atoms into the cosmos. This is how the universe builds itself, not through creation from nothing, but through transformation, through recycling. Every atom in your body, every carbon in your DNA, every oxygen in the water you drink was made inside a star. And most of those atoms were released not in a violent supernova, but in the gentle stellar winds of red giants. Stars that gave themselves away, atom by atom, over hundreds of thousands of years. It's a kind of gift quiet and unnoticed happening right now in thousands of red giants across the galaxy. Scientists suggest that about 70% of the elements heavier than helium in the universe, excluding those made in supernovae, come from the winds of red giants and the planetary nebulae they create. That includes most of the carbon on Earth, most of the nitrogen in our atmosphere, much of the oxygen we breathe. Red giants are factories of complexity, and their winds are the delivery system, spreading that complexity across light years, seeding the galaxy with the raw materials of future worlds. But here's something people often misunderstand. The stellar wind doesn't blow because the star is exploding. It's not a blast or a burst. It's a steady flow, relentless but gentle, driven by radiation and pulsation, not by violence. If you could somehow stand at the edge of a red giant's atmosphere, you wouldn't feel a gust of air. You'd barely feel anything at all. The density is so low, the particles so spread out that it's closer to a vacuum than to any wind you've experienced on Earth. And yet, over time, that almost nothing carries away entire solar masses of material. It's the patience of it that's striking. The wind blows for millennia, never stopping, never speeding up, just flowing, always flowing. In our sun's future, about 6 to 7 billion years from now, this will happen. The sun will swell into a red giant, its surface cooling its core, burning helium. And it will begin to lose mass. Not catastrophically, but steadily, over hundreds of millions of years. The solar wind will strengthen 1,000-fold, 1,000,000-fold. The outer planets, Jupiter, Saturn, Uranus, Neptune, will be bathed in that wind, their atmospheres stirred and eroded by the stream of particles. The Earth, if it still exists, will be long dead, its oceans gone, its surface molten or vaporized. And the sun will just keep giving itself away, shedding layer after layer, until only a small, dense core remains glowing white-hot and fading slowly into darkness. There's something almost meditative about stellar winds. They're not dramatic, not flashy. They don't make headlines, but they're happening constantly all around us in stars we can't even see. Right now, this moment, there are billions of red giants in the universe quietly losing themselves, breathing out into the void, returning what they took from the cosmos when they were born. It's a kind of cosmic exhale, slow and steady and eternal. Do you ever think about how much of the universe is in motion, even when it looks still? Stars aren't static. They're breathing, pulsing, losing mass, transforming. The sky isn't frozen. It's fluid, alive with change, even if that change takes millions of years. And the stellar wind is part of that fluidity, part of the way the universe reshapes itself. Generation after generation, star after star. But the wind alone isn't the end. It's a prelude. Because once a red giant has lost enough mass, once its outer layers have thinned and drifted away, something else happens. The core, no longer insulated by kilometers of gas, begins to heat the remaining material. The star enters a new phase, a phase of double burning, of thermal pulses of instability and brilliance. And in that phase, the heaviest elements a star like the sun can create are forged. That phase, that final act of fusion, is where the story deepens. And it's waiting for us just ahead in the quiet chaos of the asymptotic giant branch. There comes a moment in a red giant's life when burning once is no longer enough. The helium in the core runs out just as the hydrogen did billions of years before. The core contracts again, growing hotter, denser, but this time, there's no flash to save it, no sudden ignition to push back against gravity. Instead, the star finds another way to survive. It begins to burn in layers like a candle with two wicks, one above the other. Helium fuses in a thin shell around the inert carbon-oxygen core. Hydrogen fuses in another shell above that. Two fires burning simultaneously, feeding the star's fading light. This is the asymptotic giant branch, or AGB, the final phase before the outer layers are lost entirely. And it's here in this double burn that stars create some of the heaviest, strangest elements in the universe. Picture the structure of an AGB star. At the very center sits a core of carbon and oxygen, the ash left behind from helium fusion. That core is inert, not burning, just sitting there compressed by the weight of everything above it. Surrounding the core is a shell where helium is still fusing into carbon and oxygen through the triple alpha process. Above that is another shell where hydrogen is fusing into helium. And above that, a vast envelope of hydrogen and helium, cool and diffuse, stretching millions of kilometers into space. The star is layered like an onion, each shell burning at a different temperature, a different rate, creating a delicate, unstable balance. Scientists suggest this structure is one of the most complex configurations a star can achieve without collapsing or exploding. The double shell burning doesn't happen smoothly. The helium shell in particular is unstable. It burns in pulses, sudden bursts of fusion that release enormous amounts of energy in just a few hundred years, then quiet down for thousands or even tens of thousands of years before the next pulse. These are called thermal pulses, and they're one of the defining features of the AGB phase. During a thermal pulse, the helium shell suddenly ignites with tremendous intensity, releasing energy that causes the star to brighten and the outer layers to expand. The pulse can increase the star's luminosity by a factor of 10 or more for a brief time. Then, as the helium runs low again, the burning subsides, the star dims, and everything settles back into a quieter state until the next pulse. Research shows that a typical AGB star might experience dozens of these thermal pulses over the course of a few 100,000 years. Each pulse is like a hiccup, a sudden release of pent-up energy that shakes the entire star. And with each pulse, material from deep inside the star gets dredged up to the surface. The convective currents in the outer envelope reach down into the layers where fusion is happening and carry freshly made elements upward. Carbon, nitrogen, oxygen elements that were created in the core or the shells rise to the surface and mix with the hydrogen-rich atmosphere. The star's composition changes. It becomes enriched in heavy elements. And when the stellar wind carries that atmosphere away, those elements are released into space. This process is called dredge-up, and it's how the universe gets many of its heavy elements. Without dredge-up, the carbon and oxygen created in the cores of red giants would stay locked away, eventually collapsing into a white dwarf where they'd sit for billions of years, cooling slowly, never contributing to the next generation of stars. But dredge-up brings those elements to the surface where the wind can carry them away. It's a kind of cosmic recycling, turning the waste products of fusion into the building blocks of future worlds. But the AGB phase creates more than just carbon and oxygen. During the thermal pulses, something even stranger happens. Neutron subatomic particles with no electric charge are released through certain nuclear reactions in the helium-burning shell. Those neutrons are captured by atomic nuclei, adding to their mass, transforming them into heavier elements. This is called the S process, the slow neutron capture process. And it's responsible for creating about half of all elements heavier than iron in the universe. Elements like strontium, yttrium, barium, lead. Elements that can't be made through normal fusion because they require neutron capture, a process that only happens in very specific conditions. The cores and shells of AGB stars are one of those conditions. Let's trace this carefully. Imagine an iron nucleus, one of the most stable elements in the universe, sitting in the helium-burning shell of an AGB star. A free neutron passes by and gets captured by the iron nucleus. The iron becomes a heavier isotope of iron. If it captures enough neutrons, it becomes unstable and undergoes beta decay, where a neutron transforms into a proton, turning the iron into cobalt. The cobalt captures more neutrons, becomes nickel, and so on, climbing up the periodic table one step at a time. This process is slow, taking thousands of years for each step, which is why it's called the S process. And it only works because AGB stars produce neutrons at just the right rate, fast enough to build heavy elements, but slow enough that the nuclei have time to decay and stabilize before capturing the next neutron. The physicist who first worked out the details of the S process was Fred Hoyle, the same man who predicted the helium flash and the triple alpha process. In 1954, Hoyle, along with Jeffrey and Margaret Burbidge and William Fowler, published a landmark paper known as B squared FH, after the initials of the author's last names. That paper laid out the theory of stellar nucleosynthesis, showing how elements are created inside stars through fusion and neutron capture. It was one of the most important papers in the history of astrophysics, and it explained for the first time where the elements that make up planets and life actually come from. Not from the Big Bang, which only created hydrogen and helium, but from the cores of dying stars. Hoyle never won the Nobel Prize for this work, though Fowler did in 1983. Some believe Hoyle was overlooked because of his controversial views on other topics, or because the Nobel Committee didn't fully appreciate his contributions at the time. But his legacy is undeniable. Every time you hold a piece of metal, every time you look at the lead in a battery or the barium in a medical imaging scan, you're holding atoms that were made inside an AGB star through the S process. Hoyle gave us the map to our own atomic origins. AGB stars are also where most of the carbon in the universe comes from. Carbon is the fourth most abundant element in the cosmos, after hydrogen, helium, and oxygen, and the vast majority of it was made in the helium-burning cores and shells of red giants. When you think about carbon, you might think about diamonds or graphite or the carbon dioxide you exhale. But carbon is more than that. It's the backbone of every organic molecule, every protein, every strand of DNA. Life as we know it is carbon-based. And carbon, almost all of it, came from stars, like these stars in their final, unstable, pulsating phase, creating and releasing carbon atom by atom. There's a star called R Sculptoris, about 1,500 light-years away, that gives us a beautiful view of what happens during the AGB phase. Observations from the ALMA telescope show that R Sculptoris is surrounded by a spiral pattern of gas and dust, created by the star's thermal pulses and its slow rotation. Each pulse ejects a shell of material, and because the star is rotating, those shells spiral outward like water from a spinning sprinkler. The result is a stunning geometric pattern, a kind of cosmic fingerprint left by the star's dying breaths. R Sculptoris is also enriched in carbon, so much so that it's classified as a carbon star. A star where there's more carbon than oxygen in the atmosphere. Carbon stars glow with a deep red hue, and their winds carry carbon dust into space dust that can eventually clump together to form the building blocks of planets. Some believe carbon stars are responsible for much of the carbon in our own solar system. The carbon in your body and the wood of trees and the coal buried underground might have been ejected from a carbon star billions of years ago, drifted through space mixed with other material, and eventually ended up in the cloud that collapsed to form the sun and planets. It's a long, slow journey, but the atoms don't mind. They have time. The AGB phase doesn't last long, not in cosmic terms. For a star like the sun, it might last a few 100,000 years, maybe 1,000,000 at most. More massive stars might spend only tens of thousands of years in this phase. But during that time, the star undergoes profound changes. It pulsates, brightens, dims, ejects, shells of gas, enriches the interstellar medium with carbon and heavy elements, and slowly loses mass until the outer envelope becomes so thin, so tenuous that it can no longer sustain itself. And when that happens, when the last of the hydrogen and helium drifts away, the core is finally exposed, small, hot, dense, glowing with the last heat of fusion. And that core, that remnant, will light up the gas around it in one of the most beautiful displays in the universe. But we're not there yet. Right now, in this moment of the AGB phase, the star is still burning, still pulsing, still giving itself away. The double fire in its heart helium and hydrogen burns on creating and destroying, building, and scattering, holding the star together for just a little while longer. It's a kind of desperation, a refusal to give in to gravity, even as the fuel runs low. And in that desperation, in that final burst of fusion, the star creates the elements that make worlds possible: carbon for life, barium for medicine, strontium for fireworks, lead for batteries, all of it made in the layered shells of dying stars, all of it scattered by the wind, all of it waiting to be gathered again into new stars, new planets, new chances. Have you ever considered that the elements in your bones were made under unimaginable pressure and heat in the shells of a star that died before the sun was born? It's not metaphor, it's physics. The calcium in your teeth, the iron in your blood, the carbon in your cells, all of it passed through the double burn of an A-G. B star was dredged to the surface, carried away by a stellar wind, drifted through space for millions of years, and eventually found its way to you. You are made of stellar ash, and that ash was created here in this phase, in the quiet, pulsing final act of stars, like the one our sun will become. The AGB phase ends not with a collapse, but with a shedding. The outer layers, already thin and loosely bound, finally detach. The stellar wind strengthens the thermal pulses, become more violent, and over a few thousand years, the envelope drifts away entirely, leaving only the core behind. And when that happens, when the core is exposed to space, it heats the drifting gas with ultraviolet light, ionizing it, making it glow in brilliant colors. The star transforms from a red giant into something utterly different, something luminous and ephemeral and heartbreakingly beautiful. That transformation, that final bloom of light, is where we're heading now. Death, in the language of stars, doesn't always look like darkness. Sometimes it looks like petals unfolding in space, glowing rings of green and blue, and red clouds of ionized gas shaped like butterflies. Hourglasses, eyes staring back at the cosmos. These are planetary nebulae, and despite the name, they have nothing to do with planets. They're the final exhalation of dying stars, the outer layers cast off and illuminated by the tiny, brilliant core left behind. For a few thousand years, maybe 10,000, maybe 50. The nebula glows shimmering with colors no artist could imagine before fading slowly into the dark. It's the most beautiful goodbye the universe knows how to give. The name Planetary Nebula is a historical mistake, one that stuck long after astronomers realized their error. In the late 1700s, when William Herschel first observed these objects through his telescope, they appeared as small, round, greenish disks, not unlike the planets Uranus and Neptune. Herschel, the same astronomer who discovered Uranus in 1781, called them planetary nebulae to distinguish them from other fuzzy objects in the sky. But they're not planets. They're not even solid. They're shells of gas expanding outward at tens of kilometers per second, lit from within by a dying star. The name persisted even as our understanding changed, because that's how science works sometimes. The old words carry the weight of discovery, even when the discoveries prove them wrong. Let's trace how a planetary nebula forms. We left the star in the AGB phase, pulsing with thermal flashes, losing mass through a powerful stellar wind, shedding its outer layers atom by atom. Over hundreds of thousands of years, the envelope grows thinner, more diffuse, until finally it can no longer hold itself together. The last remnants of hydrogen and helium drift away, leaving the core exposed. That core, made of carbon and oxygen, is small, only about the size of Earth, but it's incredibly hot, glowing at temperatures of 100,000 degrees Celsius or more. It's no longer fusing anything. The fusion has stopped, but the core is still radiating the leftover heat from billions of years of nuclear burning. And that heat is now pouring directly into the surrounding gas. The ultraviolet light from the core ionizes the atoms in the drifting envelope, stripping away their electrons. And when those electrons recombine with the atoms, they emit light. The nebula begins to glow. Scientists suggest that the colors we see in planetary nebulae depend on which elements are present and how energized they are. Hydrogen emits red light when it recombines. Oxygen emits green and blue-green. Nitrogen and sulfur add shades of red and orange. The result is a spectrum of colors layered across the nebula, each one corresponding to a different element, a different temperature, a different region of space. Looking at a planetary nebula is like looking at a chemical map of a star's outer layers, frozen in time and space, glowing for anyone who cares to look. One of the most famous planetary nebulae is the Ring Nebula, also known as M57, about 2,000 light-years away in the constellation Lyra. It's visible through even a small telescope, a delicate smoke ring hanging in the summer sky. Research shows that the Ring Nebula is about 1 light-year across and still expanding at around 20 kilometers per second. At the center sits a white dwarf, the exposed core of the star, glowing at about 120,000 degrees Celsius. That white dwarf is incredibly small, only about 60% the mass of the Sun, but compressed into a sphere the size of Earth. It's so dense that a teaspoon of its material would weigh several tons, and yet it's no longer burning. It's just radiating, slowly cooling over billions of years, lighting up the nebula around it like a lamp inside a lantern. The ring. Nebula wasn't always a ring. When it first formed, it was likely a sphere, a shell of gas expanding evenly in all directions. But because we're looking at it from a specific angle, and because the shell is denser at the edges than in the center, it appears as a ring. It's a projection effect, like looking at a donut from the side. If you could move around the Ring Nebula orbit, and see it from different angles, it would change shape, revealing its true three-dimensional structure. But from Earth, from our single vantage point, it's a ring, delicate, glowing, ephemeral. Another stunning example is the Helix Nebula, sometimes called the Eye of God, about 650 light-years away in the constellation Aquarius. The Helix Nebula is one of the closest planetary nebulae to Earth, which means we can see it in incredible detail. Observations from the Hubble Space Telescope reveal intricate structures within the nebula, thousands of small knots and filaments of gas, each one shaped by the stellar wind and the radiation from the central white dwarf. The nebula is about 5 light-years across, still expanding, still glowing. It looks like an eye staring back at us, vast and unblinking, a reminder that even in death, stars leave something behind. Then there's the Cat's Eye Nebula, NGC 6543, about 3,000 light-years away. The Cat's Eye is one of the most complex planetary nebulae ever observed, with multiple concentric shells, jets, and arcs of gas, all created by different episodes of mass loss from the dying star. Scientists suggest that the central star may have been part of a binary system, with a companion star influencing the shape and structure of the nebula. The intricate patterns we see might be the result of the 2 stars orbiting each other, their gravitational interaction sculpting the ejected gas into spirals and loops. The Cat's Eye is a reminder that planetary nebulae aren't always simple spheres. They can be messy, asymmetric, shaped by rotation, magnetic fields, companion stars, or chaotic outflows. The universe is rarely as tidy as we'd like it to be. One of the common misconceptions about planetary nebulae is that they're rare or exotic. In truth, they're a natural stage in the life of almost every star between 0.8 and 8 solar masses. That includes the Sun. That includes billions of other stars in the Milky Way. Right now, there are an estimated 10,000 to 20,000 planetary nebulae in our galaxy, glowing quietly in the dark, each one marking the death of a star. Most of them are too faint or too far away to see with the naked eye, but they're there scattered across the spiral arms remnants of stars that lived and died over billions of years. Planetary nebulae don't last forever. The gas they're made of is expanding, spreading out, thinning. Eventually, it becomes so diffuse that it merges with the interstellar medium, the thin soup of gas and dust that fills the space between stars. Research shows that most planetary nebulae fade and disperse within 10,000 to 50,000 years. That's almost nothing in cosmic terms, a blink of breath. But while they last, they're luminous, visible across vast distances, contributing to the light of galaxies. And when they fade the material, they contain the carbon, nitrogen, oxygen, and heavier elements created in the star's core, and shells becomes part of the raw material for future stars and planets. There's a deep irony here. Planetary nebulae are created by death, but they're some of the most vibrant, colorful, life-affirming objects in the universe. They don't mourn the star that made them. They celebrate it. They take the star's final breath and turn it into art, into light, into a legacy that lasts for thousands of years. It's as if the universe is saying that endings don't have to be dark. They can glow, they can shimmer, they can be beautiful. The astronomer who first cataloged many of these nebulae was Charles Messier, a French astronomer in the 18th century. Messier was hunting for comets, but he kept finding these fuzzy comet-like objects that didn't move. Frustrated, he made a list of them so he wouldn't confuse them with real comets. That list, the Messier catalog, includes 110 objects, many of them planetary nebulae, and it's still used by astronomers today. Messier had no idea what these objects were. He couldn't have known that he was cataloging the dying breaths of stars. He just wanted to avoid wasting time on things that weren't comets. And yet, his catalog became one of the most important resources in astronomy, a guide to some of the most beautiful structures in the night sky. Think about the central white dwarf for a moment. It's no longer a star in the traditional sense. It's not fusing anything. It's just sitting there, glowing, radiating leftover heat. And yet, it's lighting up an entire nebula, a cloud of gas light years across, making it visible from thousands of light years away. That's the power of ultraviolet light, of ionization, of quantum mechanics doing its quiet work in the dark. The white dwarf doesn't have to do much. It just has to be hot. And because it's hot, because it's pouring out ultraviolet photons, the nebula glows. Some believe that when our sun becomes a planetary nebula about 7 billion years from now, it will be one of the brightest objects in the galaxy, at least for a few thousand years. The nebula will expand outward from where the Earth used to be, carrying with it the last traces of the planets, the asteroids, the comets, everything that once orbited the sun. And somewhere maybe on a planet orbiting another star, someone might look up and see a new nebula in the sky, glowing green and blue, and they won't know that it was once a solar system, once a place where life existed. They'll just see the light. Planetary nebulae are also laboratories for understanding chemistry and physics. Because the gas is so thin and the conditions so extreme, atoms behave in ways they never would on Earth. Forbidden lines, spectral emissions that only happen in low-density environments, show up in planetary nebulae all the time. These are transitions that are forbidden by the normal rules of quantum mechanics under Earth-like conditions. But in the near vacuum of a nebula, where atoms almost never collide, they're allowed. Observing these forbidden lines helps scientists understand the composition, temperature, and density of the nebula, which in turn helps us understand the life cycle of stars. Do you ever wonder what it would be like to witness the formation of a planetary nebula in real time? Of course you can't. It takes thousands of years. But if you could somehow speed up time, compress millennia into minutes, you'd see the star's outer layers peel away like a flower, opening the gas, spreading outward, glowing as the ultraviolet light from the core reaches it, brightening, shimmering, expanding until it fills the sky. And then slowly it would fade, the light dimming as the gas spreads too thin to glow the white dwarf, cooling the nebula, dissolving into the interstellar medium. It would be the most beautiful thing you'd ever see. and it would be gone before you could fully understand it. Planetary nebulae are where stars say goodbye, but they're also where stars give their final gift. The carbon, oxygen, nitrogen, all the elements forged in the core, and shells are now free drifting through space, ready to be gathered into new clouds, new stars, new worlds. Without planetary nebulae, the universe would be poorer, less diverse, less able to create complexity. They're not just the end of a star. They're the beginning of everything that comes next. And when the nebula finally fades, when the gas disperses and the light dims, all that's left is the core. Small, dense, cooling, slowly in the dark. That core, that white dwarf, is where the story almost ends. Almost. Imagine something as massive as the sun, compressed into a sphere the size of Earth. A ball of carbon and oxygen so dense that a single teaspoon of its material would weigh as much as an elephant. Hot enough to glow white, blue-white, hotter than almost any normal star, and yet no longer burning. No fusion, no fire, just heat, leftover heat from billions of years of nuclear reactions radiating slowly into the void. This is a white dwarf, the final resting state of stars. Like our sun, the ember left behind when the red giant phase ends. And it will sit there cooling, dimming, for longer than the universe has existed so far, fading so slowly, that by the time it goes dark, the galaxies themselves might be gone. White dwarfs are strange objects existing at the boundary between what we think of as matter and what physics allows matter to become. They're not held up by thermal pressure the way normal stars are. They're held up by something called electron degeneracy pressure, a quantum mechanical force that arises when electrons are packed so tightly that they resist being squeezed any further. It's the same principle that prevents atoms from collapsing under normal conditions. But in a white dwarf, it's pushed to an extreme. The electrons are pressed so close together that they obey the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state. The electrons push back not because they're hot, but because the laws of quantum mechanics forbid them from getting any closer. This pressure is what keeps a white dwarf from collapsing into something even denser, something darker. Scientists suggest that white dwarfs represent the endpoint for about 97% of all stars in the universe. Every star with a mass between roughly 0.5 and 8 times the mass of the Sun will end its life as a white dwarf. More massive stars explode as supernovae, leaving behind neutron stars or black holes. Less massive stars, the red dwarfs, burn so slowly that none have ever reached the end of their lives yet. But the vast majority of stars, the sun-like stars, the ones that live for billions of years and die quietly, become white dwarfs. It's the most common stellar graveyard in the cosmos. Let's trace the formation carefully. After the planetary nebula disperses, after the outer layers have drifted away, and the glowing shell has faded into the interstellar medium, all that remains is the core. That core is made of carbon and oxygen, the products of helium fusion during the red giant and AGB phases. It's no longer fusing anything. The temperature and pressure aren't high enough to ignite carbon fusion, which would require temperatures of around 600 million degrees Celsius. The core just sits there, a ball of inert matter, held up by electron degeneracy pressure. And because it's so hot, because it still carries the thermal energy from billions of years of fusion, it glows. It radiates. It becomes a white dwarf. The surface temperature of a newly formed white dwarf can exceed 100,000 degrees Celsius, far hotter than the sun. But because it's so small, only about the size of Earth, its total luminosity is much lower. Surface area matters. A white dwarf might be incredibly hot, but it's radiating from such a small area that it appears faint, even dim, compared to a main sequence star. Over time, billions of years, the white dwarf cools. It radiates its heat into space, slowly, steadily, with no source of energy to replenish it. The temperature drops. The color shifts from blue-white to yellow, then orange, then red. Eventually, after trillions of years, it will cool to the point where it no longer emits visible light at all. It will become a black dwarf, a cold, dark sphere of carbon and oxygen drifting silently through space. But here's the thing. The universe is only 13.8 billion years old. Research shows that even the oldest white dwarfs, the ones that formed when the universe was young, are still glowing. They've cooled, yes, but they haven't gone completely dark. The cooling process is so slow that it will take tens of trillions of years, maybe 100 trillion years, for a white dwarf to become a black dwarf. By that time, most stars will have burned out. Most galaxies will have drifted beyond the observable horizon. The universe will be cold dark, dominated by black holes and dead stars. And in that deep future, black dwarfs will be the most common objects in existence, silent monuments to stars that once burned bright. One of the first white dwarfs ever discovered was Sirius B, the companion to Sirius, the brightest star in our night sky. In 1844, the German astronomer Friedrich Bessel noticed that Sirius was wobbling slightly in its motion across the sky, as if something invisible was tugging on it. He predicted the existence of a companion star, too faint to see, but massive enough to affect Sirius's motion. In 1862, the American telescope maker Alvin Graham Clark, while testing a new telescope, spotted a faint point of light near Sirius. It was Sirius B, the predicted companion. When astronomers measured its spectrum, they were shocked. Sirius B was incredibly hot, around 25,000 degrees Celsius, but also incredibly faint. The only way that made sense was if it was incredibly small. It was the first white dwarf ever confirmed, and it changed our understanding of stellar evolution forever. Sirius B has about the same mass as the Sun, but it's only about the size of Earth. Its density is almost incomprehensible. A cubic centimeter of white dwarf material, about the size of a sugar cube, would weigh roughly 1 metric ton here on Earth. If you could somehow stand on the surface of Sirius B, the gravity would be so intense that you'd be crushed instantly. The surface gravity of a white dwarf is hundreds of thousands of times stronger than Earth's. Nothing we know, no structure, no material, could withstand that force. And yet, the white dwarf itself holds together, supported by the quantum pressure of its electrons. There's a limit to how massive a white dwarf can be. In 1930, a young Indian physicist named Subramanian Chandrasekhar, on a ship traveling from India to England, worked out the mathematics of white dwarf structure. He discovered that if a white dwarf's mass exceeds about 1.4 times the mass of the Sun, electron degeneracy pressure can no longer support it. The gravity becomes too strong. The electrons are forced to combine with protons forming neutrons, and the white dwarf collapses into a neutron star, or in some cases, it undergoes a catastrophic explosion known as a Type 1a supernova. This critical mass is called the Chandrasekhar limit, and it's one of the most important numbers in astrophysics. Chandrasekhar was only 19 years old when he made this calculation. He later won the Nobel Prize for this work in 1983, more than 50 years after his discovery. His achievement is a reminder that some of the deepest truths about the universe can be found not in observations, but in mathematics. The Chandrasekhar limit has profound implications. It means that white dwarfs are stable only up to a certain mass. If you try to add more material to a white dwarf through accretion from a companion star, for example, it will eventually reach the limit and either collapse or explode. Type 1. A supernovae, which occur when white dwarfs exceed the Chandrasekhar limit, are among the most luminous explosions in the universe. They're so bright and so consistent in their brightness that astronomers use them as standard candles to measure cosmic distances. In the 1990s, observations of distant Type 1, a supernovae led to the discovery that the expansion of the universe is accelerating, driven by something we now call dark energy. White dwarfs, these quiet fading embers, helped us discover one of the biggest mysteries in cosmology. But most white dwarfs don't explode. Most just cool quietly in isolation. Let's think about the Sun's future. In about 5 billion years, the sun will exhaust its hydrogen swell into a red giant, fuse helium in its core, shed its outer layers in a planetary nebula, and leave behind a white dwarf. That white dwarf will have about 54% of the sun's current mass compressed into a sphere roughly the size of Earth. It will glow at perhaps 100,000 degrees Celsius blue-white and brilliant, lighting up the remnants of the solar system. Over the next billion years, it will cool to 20,000 degrees, then 10,000, slowly fading from blue to white to yellow. After 10 billion years, it will be cooler than the sun is now glowing a dull red. And after 100 billion years, it will be barely visible, a faint ember in the dark. But it will still exist, still there, still cooling. Have you ever thought about what happens to the planets around a white dwarf? Most are destroyed when the star becomes a red giant, engulfed or vaporized by the expanding envelope. But some survive. Some planets, especially those far from the star, endure the transformation and continue to orbit the white dwarf. Research shows that astronomers have detected debris disks around some white dwarfs, rings of dust and rocky material, the shattered remains of planets and asteroids that were torn apart by the intense tidal forces. In some cases, the white dwarf is actively accreting this material, pulling it down onto its surface, contaminating the star's pure carbon and oxygen composition with heavier elements like silicon, iron, magnesium. By studying the spectrum of these polluted white dwarfs, scientists can learn what the destroyed planets were made of. It's a kind of stellar autopsy, piecing together the history of a dead solar system. One such white dwarf is WD 1145 plus 0, 17, about 570 light-years away. Observations show that it's surrounded by a cloud of dusty debris, and every few hours the light from the white dwarf dims slightly as chunks of rocky material pass in front of it. These are thought to be the fragments of a disintegrating asteroid or minor planet, slowly being pulled apart by the white dwarf's gravity and spiraling inward. Watching this process gives us a glimpse of what might happen to the remnants of our own solar system billions of years from now, when the sun is a white dwarf and the planets, or what's left of them, are drifting in slow decay. Some believe that white dwarfs could, in theory, host life, not on their surfaces where the gravity and heat would make any form of complex chemistry impossible, but on planets orbiting them. A white dwarf doesn't produce much light, but it does radiate heat. A planet in close orbit, close enough to absorb that heat, could potentially be warm enough for liquid water. The habitable zone around a white dwarf is much closer than around a main sequence star, but it exists. And because white dwarfs cool so slowly, that habitable zone could remain stable for billions of years, far longer than the main sequence phase of most stars. It's speculative, maybe unlikely, but not impossible. In the far future, when most stars have burned out, white dwarfs might be the last warm places in the universe, the last refugees for complexity and life. White dwarfs also crystallize. As they cool, the carbon and oxygen atoms in their cores begin to arrange themselves into a crystalline lattice-like diamond. Research shows that the cores of cooler white dwarfs are likely solid giant spheres of crystallized carbon, essentially enormous cosmic diamonds. In 2019, astronomers studying a white dwarf called BPM 37093, nicknamed Lucy after the Beatles' song Lucy in the Sky with Diamonds, confirmed that its core had likely crystallized. It's one of the largest diamonds in the known universe, a 10 billion trillion carat gemstone, slowly cooling in the dark. It's beautiful, in an abstract, unreachable way, a reminder that even in death, stars create structures of extraordinary elegance. Do you ever wonder what it would be like to visit a white dwarf? Of course you couldn't. The gravity would kill you instantly. But if you could somehow hover above its surface, protected by some impossible technology, you'd see a smooth, featureless sphere glowing white or blue or yellow, depending on its age, with no atmosphere, no weather, no features at all. Just a perfect dense ball of matter radiating heat into the void. And you'd feel the weight of it, the sheer gravitational presence, the sense that You were standing near something that had compressed an entire star's worth of matter into a space the size of a planet. It would be eerie, silent, still. The opposite of the roaring, churning chaos of a living star. White dwarfs are the end of the story for most stars, but they're also a kind of archive. They preserve in their structure and composition the history of the star that made them. The ratio of carbon to oxygen in the core tells us how long the star burned helium. The surface composition tells us whether the star lost its outer layers smoothly or chaotically. The cooling rate tells us how old the white dwarf is, which tells us when the star died. Astronomers use white dwarfs as clocks, measuring the age of star clusters and galaxies by studying the coolest, faintest white dwarfs they contain. The older the cluster, the cooler the white dwarfs. It's a subtle, elegant method, and it works because white dwarfs cool predictably, reliably, like candles burning down in slow motion. The white dwarf doesn't mark the absolute end of the transformation, though. It marks the end of light, the end of fusion, the end of anything we'd recognize as stellar activity. But it's still there, still massive, still dense, still cooling. And in that cooling and that slow fade into darkness, the white dwarf carries the memory of everything the star once was. The hydrogen it burned, the helium it fused, the carbon and oxygen it created, the planetary nebula it shed. All of it is recorded frozen in the white dwarf structure, waiting for anyone patient enough to read it. And when we look at these objects, when we study them, measure them, learn from them, we're not just learning about dead stars. We're learning about ourselves, about where we came from, about what we're made of. Because the atoms in our bodies, the carbon in our cells, the oxygen in our lungs were forged in stars that ended this way. Stars that became red giants shed their layers and left behind quiet embers cooling in the dark. There's a thought that keeps astronomers awake at night, not because it's terrifying, but because it's true. Every atom in your body, every bit of carbon in your DNA, every oxygen molecule you're breathing right now, every calcium atom in your bones was once inside a dying star. Not metaphorically, literally. The iron in your blood circulated through the core of a massive star before it exploded. The nitrogen in your proteins drifted out of a red giant stellar wind billions of years ago. You are not separate from the cosmos. You are made of it, built from the dust of stars that lived transformed and gave themselves back to the universe so that you could exist. Let's connect everything we've explored tonight into one continuous thread, one story that stretches from the birth of stars to the atoms in your hand. We began with stars in their youth, burning hydrogen steadily on the main sequence stable and bright. We watched them age running low on fuel, their cores contracting their shells, igniting swelling into red giants hundreds of times their original size. We felt the helium flash that hidden explosion in the core that no telescope can see, but mathematics proves must happen. We saw the great expansion, the paradox of stars growing larger while cooling, turning red and gentle, even as the forces inside grew violent. We followed the stellar wind as it carried mass away, atom by atom, enriching space with elements forged in fusion. We traced the double burn of the asymptotic giant branch, where thermal pulses in the S process created heavy elements like barium and strontium. We watched the outer layers peel away to form planetary nebulae, glowing shells of ionized gas lit by the exposed core. And finally, we arrived at the white dwarf, the cooling ember, the endpoint of stellar evolution for most stars in the universe, including our sun. But here's the part that ties it all together. The elements created in those red giants, the carbon from helium fusion, the oxygen from the triple alpha process, the nitrogen dredged up from the core, all of it was released into space. When the stellar wind blew, when the planetary nebula expanded and dispersed, those atoms didn't disappear, they drifted. They mixed with the interstellar medium, that thin soup of gas and dust between stars. And eventually, over millions of years, gravity pulled some of that enriched material together into new clouds, denser regions where stars could form again. Those new stars inherited the heavy elements from the old ones, And around those new stars, planets formed. Rocky planets made of silicon, iron, magnesium. Atmospheres made of nitrogen, oxygen, carbon dioxide. Oceans made of water, hydrogen, and oxygen bonded together. And on at least one of those planets, in at least one solar system, life arose. Complex chemistry, self-replication, evolution, consciousness, you. Scientists suggest that nearly every element heavier than helium in your body came from stars. Hydrogen. The most abundant element in the universe was made in the Big Bang, helium-2. But everything else, carbon, nitrogen, oxygen, phosphorus, sulfur, calcium, iron, zinc, all the trace elements that make biochemistry possible came from stellar nucleosynthesis. Some came from supernovae, the explosive deaths of massive stars. But most of the carbon, nitrogen, and oxygen, the elements that make up about 96% of your body mass, came from red giants. From the slow, patient mass loss of AGB stars. From the winds that carried enriched material into space over hundreds of thousands of years. From planetary nebulae that glowed and faded, leaving their contents scattered across light years. Research shows that the sun, and by extension, the solar system, is what astronomers call a population 1 star, meaning it's relatively rich in heavy elements compared to the oldest stars in the universe. Those ancient stars, the population 3 and population 2, stars formed from nearly pure hydrogen and helium, with almost no heavy elements at all. They couldn't form rocky planets. They couldn't form life as we know it. But when those stars died, when they became red giants and shed their enriched outer layers, they seeded the galaxy with carbon and oxygen. Generation after generation of stars lived and died, each one adding more heavy elements to the mix, until finally about 4.6 billion years ago, a cloud of gas and dust collapsed to form the sun. That cloud was about 1 to 2% heavy elements by mass, just enough to make planets, atmospheres, oceans, and eventually us. Think about the timeline. The oldest stars in the Milky Way formed about 13 billion years ago, not long after the Big Bang. They were massive, short-lived, and when they died, they enriched the galaxy with the first heavy elements. Subsequent generations of stars, smaller and longer-lived, continued the process. By the time the sun formed, billions of stars had already lived and died, each one contributing to the chemical complexity of the galaxy. The atoms in your body have been recycled through multiple generations of stars. The carbon in your hand might have been created in a red giant 8 billion years ago, released in a planetary nebula, drifted through space, got incorporated into a new star. 6 billion years ago, was released again when that star died, drifted some more, and finally ended up in the solar nebula that formed the sun and planets. You are made of ancient recycled stardust atoms that have journeyed through the galaxy for billions of years before finding their way to you. There's a phrase coined by Carl Sagan, the astronomer and science communicator, that captures this beautifully. We are made of star stuff. He said it in the 1980s on his television series Cosmos, and it's become one of the most repeated ideas in all of science. But it's not just poetry, it's physics, it's chemistry, it's the literal truth. The nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. We are a way for the cosmos to know itself, Sagan said. And he was right. When you look up at the night sky, you're not looking at something separate from you. You're looking at your origin, your history, your family. Do you ever feel small when you think about the universe? It's natural. The distances are incomprehensible. The time scales are vast. Our lives are brief, our planet tiny, our sun just one of hundreds of billions of stars in the galaxy. But here's another way to think about it. You are not small. You are the universe experiencing itself. You are the product of 13.8 billion years of cosmic evolution, of stars being born and dying, of elements being forged and scattered, of chemistry becoming biology, of simple life becoming complex. Every thought you have, every breath you take, is the culmination of processes that stretch back to the beginning of time. You are rare. You are precious. You are stardust that learned to think. Red giants are the factories that made this possible. Without them, the universe would be a simpler, emptier place. Hydrogen and helium glowing in stars, but no rocky planets. No atmospheres, no water, no life. Red giants take the raw materials of the universe and transform them into something more complex, more interesting, more alive. And they do it slowly, patiently over billions of years, shedding themselves piece by piece so that new stars, new planets, new chances for complexity can arise. It's a kind of generosity built into the physics of stellar evolution. Stars give themselves away, and in doing so, they create the possibility of everything that comes after. Let's return to our sun for a moment. Right now, it's middle-aged stable, fusing hydrogen in its core. In about 5 billion years, it will leave the main sequence. It will swell into a red giant engulfing the inner planets. It will burn helium in its core, pulsate on the AGB, shed its outer layers in a planetary nebula, and leave behind a white dwarf. That white dwarf will cool for trillions of years, slowly fading into darkness. But before it does, while it's still a red giant, it will enrich the space around it with carbon and oxygen. Those atoms will drift. They'll mix with other material. And maybe billions of years from now, they'll become part of a new star, a new planet, a new form of life. The sun's atoms, the atoms that once made up Earth, that once made up, you will continue their journey through the cosmos, recycled again and again, forever, part of the story. There's something deeply comforting about this. Death in the stellar sense isn't an ending. It's a transformation, a contribution. Red giants don't fade into oblivion. They scatter themselves into the universe, giving back what they took when they were born, enriching the galaxy for the next generation. And the same is true for us in a way. The atoms in our bodies don't belong to us. We're borrowing them for a lifetime, arranging them into patterns that think and feel and wonder. And when we die, those atoms return to the earth, to the air, to the water, and eventually over unimaginable timescales back to the stars. We're part of a cycle vast and ancient, connecting everything that has ever lived to everything that ever will. Some believe that understanding our cosmic origins changes how we see ourselves. It's hard to hold on to pettiness, division, or hatred when you realize that every person you meet is made of the same stardust, forged in the same stellar furnaces, recycled through the same cosmic processes. We're all connected, not metaphorically, but chemically, atomically. The oxygen you exhale might one day be breathed by someone on the other side of the planet. The carbon in your body might one day be part of a tree, a bird, a microbe, a future person. We're not separate. We're part of a single unbroken thread that stretches from the Big Bang to this moment and beyond. Red giants remind us that endings can be beautiful, that transformation is inevitable, that even in dying stars create the conditions for new life, new complexity, new stories. And maybe that's the lesson we can carry from this journey through stellar evolution. Nothing lasts forever, not stars, not planets, not us. But nothing is truly lost either. The atoms endure, the elements persist, and the universe, patient and vast, continues to reshape itself generation after generation, creating and destroying, building and scattering, forever in motion. We've walked through the life and death of red giants tonight, from the stable main sequence to the helium flash, from the great expansion to the stellar wind, from the double burn of the AGB to the glowing shells of planetary nebulae, and finally to the quiet ember of the white dwarf. It's a story of transformation of physics pushed to extremes of beauty born from endings. And it's a story that includes you, because you are made of this, every atom, every molecule, every breath. So, when you look up at the night sky, when you see the stars scattered across the darkness, remember this. Some of those stars are red giants, swollen and cooling, shedding their outer layers into space. Some are white dwarfs, fading slowly over trillions of years. Some are young, burning bright, just beginning their journey. And all of them, every single one, is part of the same cosmic cycle that made you possible. You are not separate from the stars. You are them, and they are you. Thank you for joining me on this quiet journey through the cosmos. Thank you for listening, for wondering, for letting curiosity guide you through the darkness. If this story brought you comfort, if it made you see the universe a little differently, I hope you'll stay for the next one. There are more stories waiting, more mysteries to explore, more connections to uncover. Until then, rest easy, dream gently, and remember that you are made of stars and the stars remember you. Sleep well, good night.